See, now I will discuss the unit 4, that is sequential circuits. Just a minute, please. Just a minute. Regarding the syllabus, don't worry. Regarding the syllabus for internal examination, whatever is covered, from that only will be given. And for some, if I will give any other topics which were not discussed, I will give you the notes for that, clear notes. So like that, and I will manage, and also evaluation will be very liberal. You will be benefited, students will be benefited like that. Okay, so and after the mid examination also I will conduct classes for the purpose of external examination. So don't worry, I will, that is my responsibility. You will not be the loser in any case. Okay, I will take care. Okay, right. So this is our first see our syllabus. See, so in the unit 3, main topics were covered. Okay, so afterwards, here are you seeing this syllabus? Hello, am I
Yes, sir.
sharing? No, okay. Am I sharing properly or not? I am just checking. Okay. Here. So the main topics were covered in the unit 3, and the structure of CPLDs, FPGAs. Here, this is here only just it will be given to you as a short notes only. So I will give the study material on this. So that is not a big problem. That is not a main topic for our subject. It's only introductions here, CPLD, FPGAs. Okay, right. Mainly now I am focusing on this unit 4 now in this class, sequential circuits. Okay, so this last 4th unit and 5th unit deal with the sequential circuits. Just a minute. So unit 4 and 5 deal with the sequential logic circuits. Right. So generally, digital circuits are categorized into 2 types. In the very beginning also, I have mentioned this concept. So we have combinational logic circuits, sequential logic circuits. Okay, these are the 2 categories of the digital circuits. Practically, a digital circuit can be purely combinational circuit, or can be a purely sequential logic circuit, or it can be both combinational and sequential. Okay, certain part will be combinational logic, and certain other part of the system will be sequential, so combination. So you can also see the example. So far what we have studied are all under the combinational logic circuits. Say for example, adder, subtractor. So you have seen those are combinational logic circuits, code converters, all those things, multiplexer, decoder, encoder, all those are combinational logic circuits. Even PROM. Recently we have discussed programmable read-only memory. That is also a combinational logic circuit. PAL, programmable array logic device, programmable logic array. Okay, all these called programmable logic devices. So the programmable logic devices are also known as combinational logic circuits. So another important part of the digital circuit is category is sequential logic circuits. Okay, so the main difference between the combinational logic circuits and sequential logic circuits is this: that in the combinational logic circuits, the outputs are entirely dependent on the inputs present at the moment. Okay, the outputs are entirely dependent on the combination of the inputs present at that moment. Okay, that's all. Okay, so that's why these are known as combinational logic circuits. Combinational means here, suppose there are three input variables. So with the three input variables, in how many ways we can apply the inputs? So based upon the combination of all these three inputs, that is one input can assume value 0 or 1. Each value can assume 0 or 1. So like that there are three input variables. So they can be applied in 8 possible ways. 8 ways, that is based upon the combination of these inputs. So output depends only on the combination of the inputs present at that moment in the combinational logic circuits. Whereas in the sequential logic circuits, the outputs depends on the past outputs also, in addition to the present inputs. Right. So when the concept of past outputs is there, when we say that the past output, when we say a past output means it gives the existence of concept of memory. It gives the concept of memory. Okay, past output itself indicates that there is some memory element available in the sequential logic circuit. Past output means so there will be some memory element, memory activity is there. Okay, whereas in the combinational logic circuits, there is no concept of memory activity is not there. But whereas in the sequential logic circuits, memory activity is there. So how this memory is being implemented? Now again, in the sequential logic circuits are again two types: synchronous sequential logic circuits, asynchronous sequential logic circuits. In the synchronous sequential logic circuits, all the any changes in the circuit will be synchronized with the application of the clock pulse. Okay, various changes in the sequential logic circuit take place on the application of a clock pulse. Only in the presence of the clock pulse, changes will take place at various points of the sequential logic circuit, synchronous sequential logic circuits. Synchronous, that is, it is in sync with the clock pulse. Chronicle means time. So here it is with respect to the time. All the changes will take place with some external timing signal. Okay, clock will control the various changes in the sequential logic circuits. Whereas in the asynchronous sequential logic circuits, the changes will depend independent of the changes will be independent of the clock signal. Okay, the changes will take place in the order that the inputs are applied. Okay, so you see here, this is the block diagram of the sequential logic circuit. See, sequential logic circuits consists of even combination circuits also and memory elements. Okay, mainly these memory elements come under sequential logic. Okay, right. So inputs are applied, see here, to the combinational circuits. Again, the outputs from the combinational circuits. So these outputs depend on the status of the memory elements also. So these memory elements preserve the previous state also. Okay, so that is here outputs depends on this external inputs as well as the status of the memory elements, because this memory elements the output of the memory elements is again fed back as input to the combinational circuits. So you see here, so here this output is depending on this input, as well as here also you have another input, no? So here also you have, so here you are getting the, this is from memory elements you are getting. Okay, this is the signal from the memory element. Okay, from memory element okay, you are getting like that, okay, from memory element. So output depends on the inputs as well as on the memory, from memory. Okay, from memory element. This is a normal any digital system which consists of both combinational and sequential logic circuits, or you can say this itself is a sequential logic circuit. Okay. Block diagram of a sequential logic circuit, you see it consists of a combinational circuit to which storage elements are connected to form a feedback path. Okay. Next. The storage elements are the devices capable of storing binary information. That means these storage elements can store one bit of binary information. That is, one bit means either it may be 0 or it may be 1. Okay, right. The binary information stored in these elements at any given time defines the state of the sequential circuit at that time. Okay, the state of the sequential circuit. Next, the sequential circuit receives binary information from external inputs. These inputs together with the present state of the storage elements determine the value of the outputs. Okay, so external already it is in this diagram. So the output depends on the external inputs as well as on the status of the memory elements. Okay, see here you can observe this. The next state of the storage elements is also a function of external inputs and the present state. See, already in the beginning itself, this was mentioned. So the next state, or let us say the output of the storage elements, is a function of external inputs as well as the present output. Okay. So here the meaning of this statement is that is nothing but output, that is present output depends on the present inputs plus past output. Okay, so the meaning of this statement is nothing but this present output depends on the present inputs plus present output, plus past output, present inputs and past outputs. Present inputs, past output. And past output. A synchronous sequential circuit is a system whose behavior can be defined from the knowledge of its signals at discrete instants of time. Synchronous key, asynchronous difference. Okay. Okay, if you so its behavior will be described in terms of the knowledge of its signals at discrete instants of time, synchronous sequential. Whereas asynchronous sequential circuit depends upon the input signals at any instant of time and the order in which the inputs change. Just the behavior of the asynchronous sequential circuit depends upon the input signals at any instant of time and the order in which the inputs change. This is the general description. Then you check actual topic will be easily understood. This is the general description. The storage elements commonly used in asynchronous sequential circuits are time delay devices. Time delay devices. Okay, that is in this. The storage elements in the asynchronous sequential circuit is different from the storage elements of the synchronous sequential circuit. That point you have to remember. The storage capability of time delay device is due to the time it takes for the signal to propagate through the device. At a temporary, actually here there is no concept of memory in the asynchronous sequential circuits. The memory is simply arising from the time it takes for the signal to propagate through the device. Okay, the signal will take some time to propagate from the device, from the input side of the device to the output side. So that time duration itself is providing a concept of storage. Okay, that memory, concept of memory. Okay, so you will understand all this after seeing the examples. Here only description, so don't worry, just from this description you won't understand. It is just outline. Okay, this is just introduction. Okay, so in practice the internal propagation delay of logic gates is of sufficient duration to produce the needed delay, so that actual delay units may not be necessary. Delay flip-flops we have separately delay flip-flops. Okay, saying the that is delay flip-flops. Okay, so that all that are not required here, it is being mentioned. Okay, in gate type asynchronous systems, the storage elements consist of logic gates whose propagation delay provides the required storage. Okay, so this is the general information. Okay, gate type asynchronous systems. Okay, asynchronous sequential systems, only logic gates will be used. So with that you have storage elements are also being constructed with those gates here. Okay, so next so that's why see in the asynchronous this is one good point. Okay, here we have, this is one good point. Okay, asynchronous sequential circuit is nothing but a combinational circuit with some kind of feedback. Okay, actually here there is no separate memory element. Okay, see in the sequential circuits we have two types, synchronous sequential logic circuit, asynchronous sequential logic circuit. In the asynchronous sequential circuit, this is nothing but a combinational circuit with some kind of feedback. Okay, so because of the feedback among these logic gates, in this asynchronous sequential logic circuits, only we have some configurations, some combinations of the various logic gates. Okay, will be there. So, and there will be a feedback path between the various logic gates. So because of this feedback, an asynchronous sequential circuit may become unstable at times. That means the output will not remain at particular state. So this is called the instability problem. Okay, So this instability problem of the in the synchronous sequential circuits creates a lot of difficulty on the designer. Okay, it is very difficult to design asynchronous sequential circuits. Whereas in the synchronous sequential circuits, there is no stability problem, instability problem. So they will not cross any difficulties during the operation. So synchronous sequential circuits are preferred compared to the asynchronous sequential circuit. That means certain function can be implemented with asynchronous mode or with synchronous mode. So what you will understand here, we can implement a given function in both modes, asynchronous mode or in synchronous mode, depending upon the particular application. Sometimes asynchronous mode is economy or suitable and speed of operation will be improved, and sometimes synchronous sequential circuit is suitable. So we will see that, right? So a synchronous sequential circuit employs signals that affect the storage elements only at discrete instants of time. See that point I told in the beginning also. So only at a particular instance of time, the changes will take place in the synchronous sequential circuit. Okay. So synchronization is achieved by a timing device called a clock generator. So clock is an important element in the synchronous sequential circuits, clock pulse. Okay. So clock generator is a circuit which will provide a periodic train of clock pulses. Right? A periodic train of clock pulses. Okay. Next, basically we will okay. What are the storage elements? Next, we will see. We will see the storage elements. Just a minute, please. Just a minute, please. Now we will study about various types of storage elements. Storage elements these are nothing but flip-flops. So here in this we have two types. One is latches. Another is flip-flops. These two are actually memory elements, but flip-flop is nothing but a latch with clock pulse. Where here there is no clock pulse. There is no clock pulse. Actually, both are the memory elements, both are the storage elements, but practically flip-flop is a useful element. Okay, so latch is a practically not a useful thing. Okay, whereas flip-flop is a practically useful thing. But here flip-flop is constructed with the help of latch. That's why we will study latch first. Okay, so we have different types of latches or flip-flops. Okay, here say SR latch, D latch, okay, D flip-flop or D latch or like that. Okay, so here also we have SR flip-flop. There is slight difference between the latch and flip-flop. Okay, JK flip-flop, T flip-flop, D flip-flop. So flip-flop is the smallest unit of memory element. Okay, flip-flop is the smallest unit of a memory device, a memory device. Okay, so it can be used to store it. It can store. It can store 1 bit of information. 1 bit of binary information. Binary information. 1 bit binary information. That is 0 or 1. Better here I will write like this. 1 bit of binary information. 1 bit and 0 is 1 bit. 1 is another bit. Okay, logic 0 or logic 1. Okay, once a bit is stored in the flip flop, it will remain permanently forever until it is changed again on some power. Okay, like first we will take up basic SR latch. Okay, and some differences are there between the latches and flip flop. We will see the differences later. First, we will discuss the SR latch. Okay, one S R latch. So this is also known as set reset. Okay, S stands for set, R stands for reset. Okay, S stands for set, R stands for reset. Set reset latch. Okay, it's a circuit diagram. So SR latch can be implemented with the help of NOR gates or with the help of can be constructed either with the two NOR gates, NOR gates, or with two NAND gates. Let us see. SR latch constructed with NOR gates and with NAND gates. Okay, first let us see with NOR gates. This is Q bar. Here there is a cross coupled. The output of this is a reset input. This input is used to set the output. Reset means 0. It will clear the output. Here the output is connected as here one feedback of this. One more feedback path from the complement output. Like this. Right? This is the Sr Latch device. Okay. So here the signal to be operated will be like this. Zero. Another. This is the input signal which is making a transition from 0 to 1. This is 0. This is 1. Okay. Right. Normally, for understanding the operation of this device, first let us see the truth table of the NOR gate. Truth table of the NOR gate. Okay. First of all, let us see the truth table of the NOR gate. Here I will write. Okay. Truth table of NOR logic gate. Say for example, like that inputs are A, B, output is Y, let us say 0, 0, 0, 1, 1, 0, 1, 1. Or NOR separate గా వేస్తాం. Okay. R కి opposite కదా. So here it is 1. Here also. Tell me, in all other cases it is 0. Is it clear? 0, 0, opposite to the OR. No? So this is a table of the NOR. Okay. Okay. Keep it aside. Just keep in the mind while describing the operation of this SR latch. Okay. Now we want to develop a truth table for this SR latch. Okay. So here, ఇది ఇక్కడ separate. Okay, forget about this one, nor okay, it will work as a background information. No. It is this is a S or Q bar. Okay, so these are the inputs. These are the outputs. So output is available in the normal form Q, or it is available in the complement form. Okay, right. So each reset input or set input can take the logic 0 as input or logic 1 as input. Okay, first, for example, here we have to assume for this operation. First, you have to assume whether this Q is at 0 or 1, like that. Okay, so in the beginning, you assume that Q is at some point, let us say the 1 and so automatically this will be 0. Okay. No. Present state. We should know what is the present state. Okay. So I am assuming that Q is 1 at the beginning and Q bar is 0. Okay. Suppose set a reset. I am applying set as 1 and this is 0. I am applying like this. Okay. So with this automatically you will get Q is 1, Q bar is 0. You see here S is 1 here, for example. S is 1. Okay. Reset is 0. So how to decide whether Q is 1 or 0? See, from the truth table of the NOR gate, what you will understand, if any one of the inputs is 1, if any one of the inputs, you see here, you observe like this. If any one of the inputs is 1, or if both the inputs are 1, then the output is said to be 0. See here, you can classify these 4 combinations into 2 parts. These 3 input combinations, these last 3 rows will be treated as one category, whereas the first row is different. Okay, when both the inputs are 0, output is 1. You see, whenever any one of the inputs is 1, please remember, when any one of the inputs, that is either A or B is 1, output will be 0. Or if both A and B are 1, output will be 0. So here, from this knowledge of the NOR logic gate truth table, here we can decide here. Say, let us say, this is NOR gate 1, NOR gate 2, let us say. Okay, gate 2. So let us come to the NOR logic gate 2, second logic gate. So here one of the inputs is 1. So automatically you can decide that Q bar will be 0. Okay. So when this is 0, so here also 0 is present. So 0, 0, both inputs are 0, 0 means automatically Q will be 1. Okay. See like this. Okay. So first operation was described like this, first combination. Okay. Next. When now these inputs are reduced to 0, for example, next నేను దీన్ని 0 చేసేసాను అంటే S ని 0 చేసేసాను ఇది కూడా R0. So when both are అంటే ఇక్కడ ఏంది these two inputs are disabled, so the outputs remain as it is. Earlier whatever is there, 1 0, so same thing will remain. You can understand this point like this. Ante set means to set the output to logic 1. Reset means to reset the output to logic 0. Their intended functions. See, two persons are there, for example. A person X, another person Y. See, some disturbance is coming from some student Babu.
Tiger undu chudalla Hargas.
Hello, please, some noise is coming from someone. Okay, let us come to our discussion. So when both are 0 0, previous status, previous state of the device will continue. Okay, that means this S is disabled, R is disabled, so they do not act. So if they do not act, whatever earlier state of the machine is there, that state will continue. So earlier state of this storage element is 1 0, so 1 0 will be continued like that. Okay, so now after coming to this, if one of the inputs is set, if the one of the inputs is enabled, say for example this is 0 and 1. So now what happens? Q will become 0 and this is 1. So now to explain this one, let us take up so here what you will understand, 0 1. Here it is 0, R is 1. Earlier we have in this state, okay, output is at so here one of the inputs is 1, so this can be decided. The output of the first NOR gate can be decided as a 0. Is it clear? Will become 0. So here 0 and here again 0. So now this will become 0 0 means it will become 1. So like this, 0 1. Right. Again both are disabled. Say 0 0 Jason. So what happens now? The same situation continue. 0 1 will continue. Right? See, earlier for 0 0 you have 1 0, but here for same 0 0 you have 0 1. That means the output is not simply dependent on the present inputs. The output is depending on the past output. The present output is depending on the past output. From this truth table, you will understand this one. So, 0, 0 same 0, 1 will continue. Next, both cannot be made one. This forbidden condition. Okay, this forbidden condition. Okay, this cannot be taken. Okay, so when 1 1 and it is 0, it is 0. So this state is forbidden. Forbidden. Okay, you cannot take this combination. It won't work. It will not work. Forbidden. Forbidden case. All right. So this is the SR latch operation. SR latch constructed with NOR gate. Okay. See how is the output? See here. How is the output? How is the input? See. So 1 0 you can apply. You can apply 0 1. Okay, or 0 0. But 1 1 you cannot apply. That is what here. Okay. Right. So next, in this any doubt, please ask. Okay. Next, SR latch constructed with NAND. SR latch constructed with NAND. Let us see its operation. This is set. This is reset. Q bar. So here it is being operated with the negative. So here it is. This type of pulses are being used here. 1 2 0 1 0. S R Q Q bar. Okay, now it is 145. Okay. I will discuss this later. Please also try to attend classes. In the evening, I want to conduct at 7 p.m. at 6:30 or 7 p.m. Okay. Tomorrow also I will conduct. Day after tomorrow also. And madam also wants to take class for you. So yeah, just for a small 5 minutes, please bear here. This operation also I will cover. Okay. For NAND gate, how is the NAND operation? NAND operation, NAND gate. Okay. NAND truth table. I will show you. To understand this one, let us see the NAND truth table. So A, B are there. Output Y 0 0 0 1 1 0 1 1. See, here it is 1. If any one of the inputs is 1, inputs is 0, output will be 1. That is a NAND gate. If both inputs are 1, it is 0. So from this, what you will understand. Okay. See here, SR. It is 1, it is 0. Okay. So here it is 1 first, then it is 0. Okay. So it will come as 0. Yeah, 1. You can verify this one. Suppose say if one of the inputs is how can we decide? Okay. If any one of the inputs is 0, then the output will be 1. See here. Here, one of the inputs, that means here this NAND gate, say this is NAND gate 1, this is NAND gate 2. For the second NAND gate, one of the inputs is 0. So automatically it can be set to 1. From the NAND gate truth table, you can decide if one of the inputs is 0 or if both the inputs are zeros. It's like this. Here, this part. Okay. If one of the inputs is 0, output will be 1. Like that. So here now it is 1. So here both inputs are 1. So automatically this will be 0. So first part is decided. Like that. Next. Next, 1 bit. So here, these are the active, low, enable inputs, active, low. Okay, here you can, one point you have to note down. Here, S and R are the active, low, enable inputs. when they are low, their intended operation will be realized. So here both are 1 1. So their intended operations will not be realized. So whatever is there available previously, they will continue. That is your 0 1, like that. Next, if it is made 0, if it is 1, now intended operation will be realized. That is S active. This is active low enable input. I told S and R are the active low enable inputs. I told active low enable inputs. So here S is made 0, R is 1. Let us check up this one. So S is made 0, here 0, and R is 1. So if one of the inputs is 0, automatically output will be 1 actually. 1 raw. So ఇది 1 కాబట్టి ఇక్కడ ఇది 1 1 1. So when both are 1 1, it will be 0. So now this will be like this 1 0. Similarly, again, if both are made 1, that is these two inputs are disabled. They are not active high enable inputs. So when logic 1 state is given for these S and R inputs, they do not perform their intended operations. Intended operation, what are the intended operations of S and R? For S, the intended operation is to set the output to logic 1. Similarly, the intended operation of the reset terminal R is to reset the output to the logic 0. But here, since these two are active low enable inputs, now because of the logic 1 state applied to them, their intended operations will not be performed. So whatever previous state are available, those will be continued. Here previous state is 1 0. So here it will be 1 0 only. 1 0. So for the same 1 1, see here, you observe. Here we have given 1 1, but outputs are 0 1. Here also we have given 1 1, but outputs are 1 0. What is the meaning here? It is depending on the previous output. Earlier, before applying 1 1 here, Q is 0, Q bar is 1. Q is 0, Q bar is 1. So based upon that, here we are getting the same thing, 0 1. Similarly, in this case, now 1 1, same thing, same 1 1, but here you are getting different outputs. Q is 1, Q bar is 1, Q bar is 0. Compared to earlier, it is exactly opposite. No? So exactly opposite here. Okay. So this here it is 0 1, but whereas here it is 1 0. Opposite. Why it is happening? It is depending on the order in which the inputs are applied. After 1 0, after the S1 or 0, you are seeing this one. Whereas here, the same 1 1 you are applying, but after this state, after S is equal to 0 and R is equal to 1. So here different. Right. But here also one forbidden state is there. Here it is, if both cannot be applied as 0 here. This one. So this is forbidden state. So actually both will become 1 here. This is forbidden state. This is called forbidden. So this point is called forbidden. You cannot apply inputs like this. So forbidden condition. This is forbidden condition. So this is about SR NAND latch. Okay. So here this problem, here this problem is a forbidden state. Okay, can be resolved with the help of another, with the help of modification of this circuit. We will see that in the next class. Okay. Okay, I will note down the roll numbers.